Cameron's not in either. Oh, well, that's a shame. Okay. All right, so I'm going to try and introduce to this class of nearly all physicists, but not quite. I'm going to try and look at some work, energy and power. It's something you've all seen before at physics A-level or physics GCSE. They're concepts that I struggle with all the time. I'm going to try and it's quite an unusual approach I'm taking to start with. If you could have the attention on me, please, Bowden. No need for calculator or phone or anything. I haven't put anything in the content library yet. Just want you concentrating on me. I'm taking it through quite an unusual approach. At the end, I will summarise it with a textbook approach. Okay, because there is discussion between educators and physicists and mathematicians about these concepts of energy. In fact, I believe the GCSE changed a couple of years ago. It is very easy just to think of energy as just this thing. It's like a numerical measure or property of an object, and you calculate its energy, and then it changes from one form to another. You know, the sort of stuff you've probably done and thought about at physics, at chemistry. I want to, in this lesson, in this introduction, show you how things like kinetic and potential energy, and we're dealing with classical mechanics, Newtonian mechanics, are simply consequences of Newton's laws. They are an accounting tool. Energy is not the fundamental concept for me, it's just an accounting tool. It's based upon, I don't know if you've heard of Richard Feynman's 6 Easy Pieces. I've got a link there to, it's not him, because this was where he did these lectures back in the 60s, but this is a physics professor doing Feynman's lecture to the original Feynman audio, which I've heard, by the way, and it's a really, even though it's like 50 years old, it's a really clear introduction to a different way of looking at energy. So we're going to try and do some of the maths deriving concepts such as kinetic energy and potential energy, and maybe help understand what it is. Some people prefer, so the point is you don't really need energy, Newtonian mechanics, you can just have Newton's laws. Or you don't really need Newton's laws. You can just have energy and some rules about energy. You don't really need both. We teach you both because very often the energy approach is much easier. Sometimes the Newton's law approach is easier. But you shouldn't be thinking of forces and energies as being two separate things that you need both of them. They're different ways of formulating the same rules. I'm very keen on the idea that the forces are what really are. Energy is just an accounting trick. Other physicists, particularly those who get into more particle physics, see energy as the underlying concept of the world, and everything else follows from that. And for many, I suppose I'm partly in this camp as well, it really doesn't matter. The mathematical results you get out of it are the same, so there's no difference between them. I don't quite buy into that because I think it changes the way you set up your experiments. You look for things if you have a different sort of model for how things go. We're not going to look at this video, but it is there. I haven't watched the video. I've listened to the audio, and it's an amazing way of getting to grips with a different way of looking at energy. I should say the fundamentals. So we're going to try. What's wrong, Alex?
Oh, it's okay. I want to give some money to it as well.
Sorry, say that again?
Fun.
Okay. So what we're going to do is, we're going to forget anything about energy that we know, please. I want you just to pretend you know nothing about energy. And we're going to take you through this derivation. I just wrote it down just this morning, so it's a bit scrappy. You're welcome to take notes if you want, but if I were you, I'd just listen. It will be placed in your content library, and you can get what you need out of it. So forget anything about energy. Pretend energy is not a thing. And we're going to launch an object as a projectile at u meters per second at an angle of theta, as we've been used to doing so often. We're going to ignore air resistance, and we're going to treat gravity as a constant. Are we happy with that? Okay. Now what mathematicians and physicists find really useful is something called an invariant. We want to measure something that stays the same regardless of the position or the time you're at. Okay. And we can think of that as a really important property of the system. And we're going to try and invent a measure that does that. Clearly, with a projectile, the height doesn't remain constant. Clearly, with a projectile, the speed doesn't remain constant, or the velocity. So what I want you to look at is my Suvat equation for projectile motion, initial velocity, velocity at times t, and that is an r, that's its position. You're really familiar with those, right? And we're just going to say, now, let's work out the magnitude of v squared. If you work out the magnitude of v squared, I hope you can see it's u cos theta squared plus u sine theta minus gt squared. Okay? And that gives you this expression, u squared cos squared theta plus u squared sine squared theta minus gtu sine theta plus g squared t squared. That is the velocity squared of the particle at any time t, the magnitude of it. Okay? And I'm also going to look at its height. Well, its height doesn't stay constant. Its height is ut sine theta minus half gt squared. And I'm going to look at 2gh, which is 2gut sine theta minus g squared t squared. Okay? And what we're pretending, is, and in a sense this is what happens, and we'll talk about sort of a tiny bit of historical background. We're pretending, what we're doing is we're just playing around with algebra. We're trying to invent a measure that stays the same. I've done it very quickly because I know what the answer is. But you've got to imagine this took some time to come up with. But look what happens. If I do v squared plus 2gh, it equals u squared cos squared theta plus u squared sine squared theta. Okay? So what does that tell us? It tells us v squared plus 2gh is this invariant quantity. It doesn't matter where the particle is, v squared plus 2gh remains the same for this projectile system. Okay? Any questions? Because understanding that is sort of really fundamental to the approach I'm taking. So we could invent this property of the system and call it v squared plus 2gh, and it would stay the same wherever the particle is. And that's got to be useful, right? To be able to say this is a number that stays the same, whatever happens, is useful. Eugene, you all right with this? Yeah. Okay, now I want to consider a completely different system. I want to consider a pulley with two masses. One is big M and one is little m. And I'm going to have big M being bigger than little m. Just a bit more obvious, isn't it? So it's going to accelerate. Little m is going to accelerate upwards with acceleration a, and big M is going to accelerate downwards with acceleration a. So I'm going to do the two force equations, the basic A-level force equations. On the big object, it's going downwards. So I have mg take away t is ma, big M's. And on the little mass, it's going upwards. So the mass weight is going downwards. So it's t minus mg equals ma with little m's. And I solve them simultaneously to find a. You've done this over and over and over before, so it should be very, very, very clear to you. And you get a equals g, big M minus little m, over big M plus little m. And if you've done physics, it may be that you've been taught that result for a pulley system. I don't know. Have you? No, good. I wouldn't want you to. I wouldn't want you to approach a pulley problem by going, I know this result at all. Okay, and we're going to consider the velocity of the particle at once the system has moved through a distance of x meters. So when little m has moved up x meters, I want to know what the velocity of the particles are. And they've got the same velocity, right? It's an inextensible string. Yeah? So initial velocity is 0. Acceleration we've worked out, gm minus m over m plus m. The displacement moved is x. Using v squared equals u squared plus 2as, I get v squared equals 2gx, m minus m over m plus m. Well, so what? I'm looking for conserved quantity in this system. Now, the reason this system is harder than the last one is I've now got two masses. Okay? This is why I've decided I need to... If I just try gx, and v squared, a bit like I did before, it doesn't take into account the fact that the masses are different. But if I work out this conserved quantity, mgx minus mgx plus half mv squared plus half mv squared, the algebra just comes out to 0. So I have found this thing that is 0 at whatever point in the system is I measure it. Okay? And that's effectively what's going on here with energy, is effectively we are looking for a measurement that stays the same regardless of what's happening. And if it doesn't stay the same, and what do you think was the concept they thought of as kinetic energy initially? What would you think, if you were trying to measure the energy of a moving object, What was the first measure and it was called something, vis viva or something? What would be the most natural way of sort of going, this somehow measures how much energy is stored in a moving object? It's, mass times velocity. Okay, and so mass times velocity, which we now call momentum, was kind of thought to be the energy of the particle. And in a sense it is. The problem with mass times velocity is it doesn't stay the same under these. So we gave up with mass times velocity, though it comes into use into another concept, and we did mass times velocity squared. We don't need the half's irrelevant, we just need the ratio as well. So mass times velocity squared is useful in this situation.
Is that line next to consider?
Consider the quantity. So I'm thinking of a measurement of the system, a bit like I did before. I'm going to work out what happens if I add all those up. Well, I know what the answer's got to be, but you've got to imagine it being after experimentation. People are looking for these quantities that stay the same. You're playing around with Newton's laws, and they find that this quantity, mgx minus mgx plus half mv squared plus half mv squared, stays the same. And so in both cases, we see that if you add up the quantities mgx and the quantities half mv squared, that stays the same. So what we kind of get to is saying, to simplify the way we talk about it, let's just call the sum of mgx as the gravitational potential energy. And the problem with this introduction is you've all got such a clear idea, or you've got an idea in your head of what energy means. But here, what I'm trying to get to is we're just going to define this mathematical thing, and we'll call it energy. And we won't expect anything more of it than that, other than it is the sum of the mgx's in this case. And likewise, the half mv squareds, the sum of those. We'll call that the kinetic energy. So what I have basically proved to you there is that something that's often taken as a fundamental law is, by definition, energy is conserved. Now, okay, it's only taking into account this sort of system with a moving particle and with gravity and what have you, no friction forces, and we'll look at that. But it's not a sort of now a strange new law of the universe. The conservation of mechanical energy, as we should call it, just follows from the definition of energy. Automatically, we have chosen our measurements of energy to be the thing that will be conserved. We wouldn't have chosen those values if it wasn't conserved. It wouldn't be useful. So we've explored until we have found the quantities that's conserved, and then it's not that surprising, is it, that energy is conserved? Because we'd never use this as a measure if it wasn't. Okay, so on a final bit on this, before we get to the sort of more standard derivation, consider an object of mass m moving at velocity u in a straight line, just make this easy, against a force F. So you've got a particle sliding along and a force F against it. And I've just done suvat there. So S, the distance moved, I'm calling x. U is the initial speed, x. The acceleration is minus F over m, isn't it? Force equals mass times acceleration. I've got the force going against the motion of the particle, so the acceleration is minus F over m. If I apply v squared equals u squared plus 2as, I get a half mv squared equals a half mu squared minus fx. Or I get a half m v squared minus u squared equals minus fx. Well, this half mv squared minus u squared, we've just defined as being this thing called kinetic energy, this mathematical thing called kinetic energy. And what we've defined, this said here, is that the change in kinetic energy is the force times the distance. Because the force and the distance are going in the opposite directions in this case, so it's minus. So here we have got something we're going to take big notes on. We've got the change in kinetic energy is the force times the distance moved. And we are going to call this work done. The change in kinetic energy is work done. So we are going to define kinetic energy as this conserved quantity, or part of a conserved quantity, and we're going to say when an object changes its kinetic energy, there is work done on it. But all of it is just a reformulation of Newton's laws. There's no new concepts involved. And that's what I want to drum in. In this derivation of energy, I haven't introduced you to a new concept, a new physical concept. It's just Newton's laws, just follows from the maths. Okay. So, that was, let's say, slightly unusual. Well, I don't know if it's unusual. It's unusual for me. It's unusual for a maths teacher to define it that way. That might be. I mean, that might be how Mr. Mansell shows it. Is it? Does it feel very different? Don't really do it because I've spoken to Mr. Mansell about this, and I think he's slightly uncomfortable with doing this because he's obviously a lot more smart and knowledgeable than me about such things. But we also, I think, have a slightly different approach to. He's one of those who thinks that the maths is the same. Like, why would you do it? It's energy, but he does confirm I'm right. I do check things with him. Confirms I'm right. It's energy or forces. There, you don't need both. At least in this realm. He doesn't think it's any point thinking of its forces. To me, I'm just looking at things and I can understand there's a force, a gravitational force coming out of it. I don't like this idea of saying actually really it's an energy what's it called, energy sort of map. Not, the gravitational wells that you'll see. It's lovely science fiction, but I think things are pulling me and I'm being pulled towards things, and that's just the way I see the world. So it helps my mental model to see that energy is just an application of those forces. I guess when you get down to other levels, it's more useful to think of it in terms of energy. But that, as you know, that's why all quantum physics is clearly wrong, because I don't understand it. So this is the textbook, or a textbook approach. I won't use that pen. Define kinetic energy. Define kinetic energy as a half mv squared. Define it like that. Okay. Define work done on an object. So these are the things you need to know. So I'm very happy for you to take notes on this. I'm very happy just to leave it. Define work done on an object as well. What did I define it as, or what do you already know it is? Let's see if Bowden.
Is it the rate of energy transferred?
Not the rate of energy transferred. No, not the rate of energy transferred.
Oh no, energy transferred is in general.
Yeah, okay, more or less. But I gave a very precise thing because I haven't talked about energy. Apart from the only form of energy I've talked about really so far is kinetic energy. No, I showed that force times distance was. Well, what did I show force times distance was? I showed that was the change in this quantity I call kinetic energy. I need to go back to that slide. Yeah. So I rearranged it and I got a half mv squared minus u squared came out there. And I have defined those as being kinetic energy, so that's the change in the kinetic energy, and I'm going to define that as the work done. The work done on an object is its change in kinetic energy. If an object does not change its kinetic energy, it has had no overall work done on it. Okay, and that does contrast slightly with the sort of understanding you may have developed through GCSE chemistry and physics. But we need it. It's not me. This is the A-level definition, the correct definition. Define work done on an object as the change in kinetic energy. Okay. This idea of potential energy, which is, let's face it, is always the one we get confused about, can best be thought of as the ability of an object to do work by virtue of its position in a system. So we often talk about an object on a hill has more potential and energy than an object at the bottom of the hill, right? But it doesn't really. It's no different from the two objects are the same. You couldn't look at that object and measure something about it and find it's buzzing with potential energy, and the one low down it is not. It's by virtue of its position in the system. It's because it's on a hill means, so it's a property of the system around it, the environment that it's in. Because it's on a hill, it would be able to fall down and increase its kinetic energy, or could increase something else's kinetic energy. So it's quite a difficult concept. But it's just a mathematical tool. While it can be helpful to think of something as possessing potential energy, it doesn't really possess anything. It's just in a certain place, which means if you let it go, this is what's going to happen because of Newton's laws. Okay. So work is... Okay, now I derived for you from definition that for a constant force, work is force times distance. And that was for constant force. Can you do the advanced math reasoning to tell me what the definition of work would be if it wasn't a constant force.
dFdt times the integral of force with respect to position.
Exactly right. Okay, so it's the integral of force with respect to position. You imagine, if you like, splitting it up into small bits of motion where lots of little dx's. It moves in little jerks. Imagine, and each little jerk, the force is constant. So you've got force times dx plus another force times dx plus another force times dx. It's integral of force dx. Okay. And that's only if the force is going... And this, by the way, is more than you will need for quite a while yet, this next bit, but I know you've been doing it in maths recently. What about if the force is not going in the same direction as the movement? Sorry?
The cosine theta.
It's cos theta. So if we have that's force, and if you've got an object that is moving along in this direction, so it's constrained to move on the dotted line, but the force is pulling it that way, but it can't move that way. So the only thing causing the motion is the horizontal component of force. That would be F cos theta, wouldn't it? Okay, from what you've done in maths recently, if we take x to be a direction, where do you get f? So what we're saying now is fx cos theta, force times distance, fx cos theta, dot product. Okay, so I'm going to give you the sort of more advanced bit, and you'll never see this again unless you are doing sort of mathematical physics at university, okay, or engineering, but it's useful. That's just going to give you the integral of fx cos theta in the direction of x. So you can, if you don't understand that at all, you can just ignore that. It equals fx cos theta for constant force, and that just equals fx if f is in direction. And all this, though I haven't justified absolutely everything, all of this has followed from our definition of energy rather than introducing a new thing called energy. That's all it is. It's a property of Newton's laws. Okay, so we're going to just discuss the conservation of mechanical energy, look at a couple of examples you'll try and exercise. Gravitational, elastic, potentials, and kinetic. This is all called, so we're looking at the conservation of mechanical energy. Gravitational potential energy, elastic potential energy, and kinetic are all mechanical energies. Okay? You all right? Yeah, yeah. Okay. And we say they are conserved by definition. From what I've shown you, all of these things must be conserved when they, because of the Newton's laws. They are conserved if the forces acting on them are circular as this, are conservative. If these are the sorts of forces that conserve energy, then energy is conserved. And if these are not the sorts of forces that are conservative, then energy is not conserved. Well, what that actually means is if you've got a force that is following Newton's second law, so it is causing an acceleration, it's a conservative force. Okay? So gravity tension. What sort of forces do we look at, do we use, where we don't analyse by looking at potential, looking at motion, because they do something else, they don't do Newton's second laws, there's not an equal and opposite reaction in the way we normally think of it. A force that you can think of as causing a loss of energy would be your usual way of thinking about it. Friction. Okay. So it's not that friction is breaking the rule, but it's a dissipative energy, because it's not, if you like, I'm trying to avoid the idea of converting from one form of energy to another, but it's not converting one form of mechanical energy to another. Unless you decide, as you could do, to take the particles that are getting hotter as a result of friction as to be part of your mechanical system. And then guess what? Mechanical energy would be conserved. So if you're looking at the whole system, if you're looking at the mechanical energy of all the particles in the system, that will be conserved. But if you take some things as not being part of the mechanical system, then it won't be conserved. Dissipative. You do need to know these words, Mr. Zong, so I hope you're paying good attention. Dissipative. Dissipates. Forces like friction are dissipative. And they are reducing the mechanical energy of the system. They are increasing, in a sense, the mechanical energies of parts of things outside the system, I suppose. I think that's right. So we have the conservation of mechanical energy. So if we just have, if only conservative forces, we can say sort of the gravitational potential energy plus elastic potential energy plus kinetic energy is constant. And remember, the work done on any one object is its change in kinetic energy. If one object in a conserved system increases its kinetic energy, something has done work on it. By Newton's laws, that means that thing has had negative work done on it by the other object. We'll see that. Okay, I think we're ready to have a look at a couple of examples. There's the textbook. So, there we go. Okay. So this may or might, I really don't know what sort of, how far you've gone with this in physics. This may seem incredibly simple, or it may not seem incredibly simple. I just don't know where you are with it, but I've just realised I need my iPad. There it is. Okay. So a bullet of mass 25 grams is fired at a wooden barrier 3 centimetres thick. When it hits the barrier, it is travelling at 200 metres per second. The barrier exerts a constant resistive force of 5,000 newtons on the bullet. Does the bullet pass through the barrier? And if so, what speed does it do so with? Now, could we have worked this out without any mention of energy whatsoever? I want you just to think about that. Could we have done this without any thought of energy whatsoever? Alex, what would we have done? I can't hear a single word you're saying. And I think that's deliberate, isn't it?
So we use SUVAT and motion.
Yeah, we could use SUVAT, couldn't we? We know what the mass of the bullet is. We know what the force is. So we can work out the acceleration of the bullet. We know the barrier is 3 centimetres thick. So we could use SUVAT for a displacement, a known displacement, a known acceleration. So we could find the speed when it comes out the other side. If that speed comes out as negative, we've obviously gone wrong somewhere, which would mean the bullet had got lodged in the barrier. Yeah. If it comes out as positive, we've worked it out. So we can do all of this without using energy. Okay. I now want to do it using energy. So initial kinetic energy equals 1/2 times 25 times 200 squared, which is 4 to 50, 100. Check my maths, please. Yeah. Yeah.
Do we need to convert to kilograms?
Oh, good man, thank you. I mean, actually, if I'd stayed working with grams all the time, it wouldn't matter, okay? But on the other hand, I was about to write joules at the end, which would have made me wrong. Thank you. Very important that you look out for those things. Sometimes it doesn't matter, but I was about to matter because I was going to write joules. So it should be 500. Okay, I've given this, by the way, units of joules. I suppose I should have mentioned that. What other units could I have used rather than joules?
kg per
Hang on, you first, yeah, Alex?
kg per amp per s. Kg per
Not per.
kg slash.
No, not slash.
Times.
Yeah.
Times m slash s. M squared slash s squared. Because you squared the speed
Mass times velocity.
squared.
Yeah.
Yeah. I think it.
Mass times velocity squared.
Yes.
So that's the units. Kilogram metre squared per second squared. We do a lot more of this later on. It's called dimensional analysis. It becomes very, very important. Okay. What is the work done on the bullet by the barrier? Okay, so this is where the energy approach looks different, and it's going to try and I'm going to try and make some of my sort of notes make sense. But we've got a constant resistive force. So if we just go, well, we've heard what work done is, it's the change in kinetic energy, and we've worked out how to calculate it.
It's like initial energy minus, final energy minus initial energy.
It is, but it will be, but I need to find what that will be to work out the final energy.
Yeah, and F times O3.
Yeah, force times the distance. What's the distance? It's 0.03. Now, you've got to be really careful with this. I try to get it right every time because I know how dangerous. I'm not saying you'd go wrong if you left it like that. But if work is done on the bullet, it means it's increasing its kinetic energy. If positive work is done on the bullet, it means it's increased its kinetic energy. This is negative work done because the force and the distance here are in opposite directions, aren't they? It's moving, or the displacement, the force and displacement in opposite directions. So that is equal to 150 joules. So by the work energy principle, so we could write it in the work energy principle form. I'm not saying you have to write it because I'm very happy with the idea that goes, well, it had 500 joules, it's had 150 negative joules done on it, so it's now got 350 joules. I'm very happy with that. In terms of the work energy principle, we might go half v squared minus u squared equals minus 150. Simply is a half times, what's the mass? 0.025. 500 squared minus u squared equals minus 150. Sorry, can you see where I went wrong there? What I've written down there? What's the initial speed? I got it the wrong way round, didn't I? Minus 2, v squared minus 200 squared. And that equals minus 150. And if you could work out what v squared is from that? So there's my shortcut, is to work out what the kinetic energy of the final bullet is. Hopefully, you're right. Has someone worked it out? If you think I've gone wrong, tell me.
Yeah, it was 52,000 to 28,000.
So what's V?
Is 167 meters.
167. So 28,000. One, say that again?
167 meters per second.
167 metres per second. Okay. Now, intuitively, it's absolutely fine just to go look. It had 500 joules of energy. It had 150 joules done against it. So now it's got 350 joules. So it's got to have a kinetic energy of 350 joules. So half mv squared equals 350. And that's fine. I'm just trying to show how it all relates to the stuff I've done. I'm just going to check the answer because I do have... yeah. Okay. So, is energy conserved? Well, what we'll say is energy is conserved by definition, but what is not conserved? Mechanical energy is not conserved. And the reason it's not conserved is there have been dissipative forces acting on it. Not conserved, sorry, not conservative. Conserved. Energy is conserved, but mechanical energy is not conserved. There have been dissipative forces. The force of going through the block, it's heating up the block, it's making sound. You could think of them all as forms of mechanical energy in terms of the motion of the particles and the molecules, but it then becomes a very difficult sort of way of solving problems. So this approach is by far the easiest. Okay. But again, there's no miracle that says energy has to be conserved. We have to find energy to be the thing that is conserved. And when we look at sort of other forms of energy, they will be defined in such a way that makes sure that they don't break the conservation of energy. Because that's all that's going on here. Okay. All right. Do you want to try this one yourself, or do you want me to work it through? Try have a little bit of a think about it first. Yes, okay. So if you've got the idea here that the total, from the approach I've taken, the total work done on the plane is zero, must be zero because it's not accelerating, it's not changing its kinetic energy. The total work done on the plane is zero, but there are two forces that are doing work on the plane. So one of them is doing work in one direction, one's doing work in the other direction. So you'll get the total work done on the object is it's changing kinetic energy. There is no change in kinetic energy, so in total no work is done on it. But there's a force pulling it through, force times distance, so it's doing work. And there's a resistance force going the other way, force times distance, so it's doing work. And those must add up to zero. This question is, if you like, a little bit back to front, because I'm telling you the work energy principle is what comes first, so of course it holds.
I understand why F and R is doing work whilst L and R.
Okay, because we looked briefly, didn't we, at the idea of it being force times the distance moved in the direction of the force. So if this force is acting forwards and the plane is acting forwards, the force is moving through a distance. So the force is doing work. Whereas lift and the weight, the object is...
Well, as it goes down, it's lifting up.
But it's not going down, it's flying on a constant line. So look at the table. Is gravity doing work on that table at the moment?
Probably not.
You don't sound very convinced. I prefer Eugene being fairly convinced with shaking his head. Gravity's not doing work on it. It's not moving. There's no move. There's a force on it. I am not doing any work on the wall when I go and push the wall. Okay? I'm pushing the wall, but the wall, unfortunately, is not moving, so there's no distance component. I am not causing any tendency to change its kinetic energy. Whereas here, it is moving. This force is going through a distance.
Okay, so because there's also distance, the other one too, there's also distance.
Yeah.
This one has work done, it's just counteracted in different ways.
Yes, so both of these forces. So there's something pulling back the plane, and there's something pushing forward the plane, and the plane is moving. So the force is moving through a distance. So the integral of force with respect to distance, which we've shown must cause a change in kinetic energy. So if you like, the way I'm looking at it is this does cause a change in kinetic energy, 9.45 times 10 to the 8, but this also causes a change in kinetic energy, minus 9.45 times 10 to the 8. Because if you take an object and it moves the distance with a force acting on it, it accelerates on Newton's laws. Whereas this is not moving in the vertical direction, so its acceleration, the vertical acceleration is zero. Okay, now the last part is a little bit harder, so I'm happy to give you some clues. This is where we really test whether you can put it together. Once you can do this, then you can tackle the problem. I can give you some clues. You can ask me questions, or you can just tell me what you think the answer is. But it does require a bit of work. It's not a do it in your head one. Are you on part 3 yet, Bowden? Yeah. Rain, how are you doing? On part 3. And of course, all of this could be done, all the problems you need could be done using Newton's laws and Suvat, except you do have to answer what's the work done, and that's something we've defined, so we do have to be able to do it. So again, it's a work energy principle, a work problem you want to do. Have you done it, Will?
Oh yeah, I worked out what the frictional force was instead of.
Okay, so you did it all through Suvat.
No, I did it through work done,
Okay.
but then I just.
What did you get as your answer? Oh, I see. You worked out the area. I'm with you. I'm with you.
My answer is
So, what did you get for
1.1 times 10 to the 10 joules.
1.1 times 10 to the 10? Well, that's a fair bit of rounding, is it?
Well, 1.1145.
Yeah. Okay. Fine. And then the average force is probably it's a different thing to work out. The average resistance force. Because it wasn't constant. The resistance force wasn't constant this time. Is that what you've missed? You've got the right answer. The work done. But the resistance force is no longer constant. Why realistically don't I think it would be constant?
Because it's a function of velocity.
Yeah.
But I don't think that affects my method.
No, good. So tell me when you've got the average resistance force as well.
Oh, I've got minus 371,500.
Okay, lovely. You can go on to the exercise if you've got that. I'll work through it with. Okay, let's go. Artem. So have you managed to crack this? No. Okay, so if you haven't solved it by now, can you pay careful attention? I'll go through in I think the best way. And then you need lots of practice. It's very new stuff to look at. Okay, by the work energy principle. Okay, what's the work energy principle, Artem?
That mechanical energy is conserved.
No. What's the work energy principle? Eugene. Right?
Work done is equal to 0.
Not quite, no. Maybe I didn't write down that it's the work energy principle. It's the thing that says the work done is the change in kinetic energy. That's the underlying principle. Maybe I didn't write it down and call it the work energy principle, which is a big mistake. I'll correct that, apologies. So, Artem, where were we? The work energy principle, the work done on something is its change in kinetic energy. So what's the work done on this plane? Okay, half what's m? It's 100,000. So whatever else has happened, we say we know that the work done on the object is changing kinetic energy. Its kinetic energy is increased, so it has a positive work done on it. And then we've got to look at those forces that are doing work on it, and that comes down. That comes to I've made it, but Will I know has got this right, so I can check. 855 times 10 to the what? 10 to the 8. See, I can't quite read what I've got here. 8.55 times 10 to the 8. Yeah, okay, yeah. There we go. Right, are we happy with that? That's the most fundamental thing. That's the definition of work done being a change in kinetic energy. Okay, now we've got to look at those things that are doing work on it, those things that are changing its kinetic energy, or trying to change its kinetic energy. That's the thrust. That's a constant force, the thrust, of 400,000. Times the distance moved by the force, which is 30,000. Okay, and that's going to be 1.2479 times 10 to the 10. I'm sounding querulous, uncertain. Confirm that, check that?
Yes.
Yeah. Okay. So, what's the work done by resistance? Well, this is using the same sort of ideas. Alex, how would we find the work done by resistance?
Oh, to find the work. Well, I will need to first find the average resistance first.
No?
Well, I would just find the difference. Oh, total work done minus the work done by.
Yeah. The total work done by resistance is given by work done on plane is equal to the work done by the thrust plus the work done by resistance. There are two things doing work on the plane. One of them is thrust, one of them is resistance. I should move that down. What's the work done by resistance? Work done on plane, rather, is 8.55 times 10 to the 8. Work done by thrust, 1.2 times 10 to the 10, plus work done by resistance. And that gives you the work done by resistance is equal to, let's see if we've got it right. By which I do mean we. I don't have a calculator. Some of you have already done this, so
1.11.
so that 1.1145 times 10 to the 10. Okay, good. Which is pretty depressing, really. It's the work done by the thrust. Seems like an awful lot of energy. Think about this, it's an awful lot of energy. And what's it doing? Almost entirely overcoming its resistance. And if the plane is going at a constant speed, all that energy is overcoming resistance. Okay. And finally, the average resistance, we can find that by realising that the work done by resistance, well, it's the integral of the resistance with respect to the distance. You've done enough. You've done the extra calculus, so you should understand when I'm talking about the mean value of an integral. That's basically this. It's the mean value of the resistance times the distance. So 1.145 times 10 to the 10 equals R times 30. And that gives us R is, I hope, 372,000 approximately. That should be negative, shouldn't it? That should be negative, and so that's negative 1.372. Okay. The resistance isn't constant, the plane is accelerating, so it's increasing its speed, so the resistance force increases as its function of velocity, air resistance. All right? Okay, so has that gone? So I'm really unclear about the syllabus these days with respect to what you do in physics. This is the first time I've taught this since the change to syllabus. Is that all very new to you? Okay, so have I gone to, you're saying it's not so new to you, Will? Is that just because you knew it anyway? Or?
I feel like we must have done it.
In a way, it doesn't do much. It doesn't go much beyond what you've done at GCSE. Almost, is it? It's sort of on the edge of being what you've done at GCSE. It's just you actually need to sort of have a deeper understanding of how to do it. So, okay, I've given you an exercise. Work on it. Next lesson, work on it, because obviously I'm going to have to catch up with Cameron and Tony. Is Cameron and Tony? Yeah, I'll catch up with Cameron and Tony next lesson and go through this. So there's an exercise for you to try. Ask any questions you want. Have I allocated you the textbooks yet? The mechanics textbooks?
Yeah.
Cool.